In the last lesson, we learned how to find the GCD of two numbers using the Euclidean algorithm. We also learned how to use the extended Euclidean algorithm to find a linear combination between those two original numbers that would add up to the actual GCD. I think you saw a couple of examples last time, and we're going to be doing this again some more here today, so you'll see it done again. But we're still working on this because we're going to go one step further here, and that's where why we're even doing this in the first place, is to get what we're going to talk about next. Then you'll find that next time, when we start talking about the RSA cryptography, you're going to need to know how to do this, and you'll already know. So let's just continue on then with this section. So one thing new in this section is finding the multiplicative inverse mod n. Now I think you know what multiplicative inverse in general is. If I have a 5 and I want the multiplicative inverse, that would be saying what times 5 gives me a 1, and that would be 1/5, because 5 times 1/5 gives me a 1. So this is similar, except that we're applying a mod n at the end. So this says a multiplicative inverse mod n, or just inverse mod n, of an integer x is an integer s such that s times x mod n will equal 1. So the product is going to equal 1 after we take mod m of that product. Okay, so for example, let's look at some examples. 3, we would say, is an inverse of 7 mod 10. Why? Because 3 times 7 mod 10 equals 1. Here's another example. The number 7 is an inverse of 5 mod 17. Because 7 times 5, that would be a 35, mod 17 equals 1. So when you multiply the two numbers together and then apply the mod, you need to end up with 1 if they're multiplicative inverses mod n. So would it be possible for a number to be its own multiplicative inverse mod n? Well, yes, because here's an example. 7 is the inverse of 7 mod 8. Because 7 times 7, which is a 49, mod 8 equals 1. So here's a case where a number is its own multiplicative inverse. So these are just examples I just pulled out of my hat just to show you. We're going to learn, though, how once you're given a number and then the mod, the n part of it, you're going to learn how to find the multiplicative inverse. So that's what this lesson is going to be about. So finding the inverse of a number mod n is a key step in the RSA crypto system that we're going to cover later. So we need to learn how to do this. So this box kind of tells us how to do that. So first of all, we're looking for the multiplicative inverse of x mod n when it exists. So x is going to be the number we're getting the inverse of, mod n. Okay, so the first bullet point says if the GCD of the two numbers x and n is not equal to 1, then x does not have a multiplicative inverse mod n. So that's a key point. The GCD between the x and the n has to equal 1 if we're even going to find a multiplicative inverse. Okay, so that's one thing to keep in mind. The next thing is this. If x and n are relatively prime, remember, what does that mean? That means that their GCD is equal to 1. Then the extended Euclidean algorithm finds the integers s and t such that 1 is equal to sx plus tn. Is that true? Yeah, remember that extended Euclidean algorithm finds a linear combination that ends up equaling the GCD. And again, the GCD would be 1 if they're relatively prime. So this is just the the result of what we would do when we apply that extended Euclidean algorithm. Now don't worry too much about that next bullet point, but let's go to the bottom line. Once we get that linear combination that we already know how to do, and you're going to see examples of that here in a minute, then we figure out one of, that linear combination. There's an S and a T. We got to figure out which one is the S, and then take S mod n. And the result of S mod n is going to be the multiplicative inverse of X mod n. So S mod n is the bottom line. As long as we can go through that extended Euclidean algorithm, find the linear combination, then find S mod n, that's our multiplicative inverse. So we're just going to do what we've done before, use that extended Euclidean algorithm. First of all, verify that the two numbers are relatively prime by finding that the GCD is 1. And if that's not the case, we say there's no multiplicative inverse. But if they are, we will end up with a linear combination of those two numbers that equals, it's the GCD, which is 1 in this case. Then the number in front of the number for which we're getting the inverse is going to be the number we're calling S. Because remember, we've got these two numbers we're getting, we've got the X and the N. So you're going to have this linear combination, and the question's going to be, which one is S and which one is T? And so here's where we're getting that information. We look to find the number in front of the number for which we're getting the inverse. So that's the X in this situation here. So the number in front of the X is what we're going to call S. And then the multiplicative inverse ends up being S mod n. Okay, so at this point, you still might be a little fuzzy, but we're going to go over an example next, and you'll see how we do it. Okay, let's say we want to find the multiplicative inverse mod 35 of 48. Okay, so we're getting the multiplicative inverse of 48 mod 35. Okay, so which one would be the X and which one would be the N? Well, the one that we're doing the mod of, so we're taking mod 35. The 35 would be the N, and the 48 would be our X. But starting out with this extended Euclidean algorithm, we're just going to take those two numbers, not worry about which one's X and which one's N, and start this extended Euclidean algorithm, which means we put the two numbers, write the two numbers down with the largest one first. Okay, so largest one first, in this case 48 is the largest, and then I'll put a 35 next to it. So let's go through that process that we already know how to do. So we're going to keep taking the mod. We're going to here first take 48 mod 35, and we end up getting a 13. Then we take the last two numbers, the 35 and the 13, go 35 mod 13 and get a 9. Then we'll take 13 mod 9 and get a 4. And then a 9 mod 4, get a 1. And a 4 mod 1 and get a 0. So we've gotten all the way down to 0. Remember, what we do to find the GCD is step back 1, and here then would be the GCD. It is a 1. So we've verified that those two numbers, 35 and 48, are relatively prime, that the GCD does equal 1. So based on what we learned on that last slide, we can now say that there is a multiplicative inverse mod 35 of 48. Okay, now let's go further using the extended Euclidean algorithm to find a linear combination of those two numbers, 35 and 48. Okay, so we remember that pattern that we used last time. We're going to come up with a bunch of equations. So we'll start with that GCD, and we'll say that equals, and then remember we're using the two previous numbers on that long line. So in this case, for the 1, we're going to write it as a linear combination of the 9 and 4 by using that, remember we called it y minus y div x times x, remember that kind of thing. Anyway, so in this case it's 1 equals 9 minus 9 div 4 times 4. And again, that's that pattern that we learned. Okay, now remember what we're going to do. We're going to only evaluate what's in the div, only evaluate that div. Leave the other numbers, you know, there. Don't try to go backwards and then say, well, 2 times 4 is an 8, and then I take 9 minus 8. You just be getting back to where you're starting. So you want to leave the 9 and the 4 there, but just evaluate the 9 div 4. 9 div 4 is a 2, so we have 9 minus 2 times 4. Now we'll go on to the next number to the left is a 4. And we're going to then use the previous two numbers of the 4, which is 13 and 9. So it would be 13 minus 13 div 9 times 9. And evaluate the div, and that 13 div 9 is a 1, so we just have 13 minus 9. And leave those as they are. 9. 9 is going to equal, and we see the two numbers in front of the 9 are 35 and 13. So 35 minus 35 div 13 times 13. And we'll evaluate the div and get this. And we'll do the same thing for 13 and evaluate the div and get this. Okay, remember our goal in this extended Euclidean algorithm is to write the GCD, which is in this case is a 1, as a linear combination of those first two numbers, 48 and 35. Okay, so that's our goal. And so that's what we're going to try to do. We're going to have to use all of these equations to come up with that. So first of all, we'll start with the one that starts with a GCD of 1. So I'm just starting with this first equation there. Okay, 1 equals 9 minus 2 times 4. But then I'm going to, I see that 4 is equal to 13 minus 9. So I'm going to replace the 4 with what I know it to be is 13 minus 9 from that second equation. Now, again, we don't want to just go and put all those numbers together again, but we need to, the key numbers that we're looking at here are that we've got now 1 as a combination of 9s and 13. So we'll, let's do some, distribute the negative 2 in. And so we could write that as 9 minus 2 times 13 plus, because a negative 2 times negative 9 is a positive, I'm sorry, negative 2 times a negative 1 is a positive 2. So I have a positive 2 times 9. So the key is I wanted 9s and 13s in there. And then whatever has to come in front of those is fine. But now I've got 1 9 at the beginning, 2 9s at the end, so I'll just combine the 9s. So I have, how many 9s were there? There were 3 9s, 1 9 at the beginning, 2 later, so there's 3 9s. And then how many 13s? We have that negative 2 of them. Okay, so now what have we accomplished? We now have 1 written as a linear combination of the 13 and the 9. So we're making progress because now it's a linear combination of those two. But we need to keep moving over so we eventually get them as a linear combination of the 48 and 35. So now, well, let's move over 1 here, and we have 13 and 9s, but now let me see if I can change the color. We know that 9 is equal to this. So we're going to put that in place of our 9. And now we've got 35 and we've got negative 2 13s. Now we'll do the distributive property here so that we end up with 3 times 35 and a negative 6 times a 13. And now combine our 13s. So we have negative 2 13s and then minus 6 13s, so that's a negative 8 of the 13s, and 3 of the 35s still. Now we have that 1 written as a combination of the 35 and the 13. So we're making progress, but we need to move back one more. So we know that 13, change to purple, 13 is equal to 48 times 35. So I'm going to put that in for 13. So I have that. I'll distribute that negative 8 in. So I have negative 8 of the 48s and a negative 8 and a negative 1 to give us a positive 8 of the 35s. Okay, so negative 8, you can look at that minus 35 as a negative 1 times a 35. So negative 8 times a negative 1 is a positive 8. Sorry, negative 8 times a negative 1 is a positive 8. So we have 835. And this is good because now we're finally to see a combination of the 48 and 35s, except we need to just combine the 35s. So there's negative 8 of the 48s, but then there are 11 of the 35s. Okay, so now we've written the GCF, sorry, I call it GCD, it's the same thing, but the book calls it a the book calls it a GCD, and I might occasionally call it a GCF. But anyway, so it's the GCD1 now has been written as a linear combination of those first two numbers. Now, what was the linear combination? We have a negative 8 in front of the 48 and an 11 in front of the 35. Now, remember that it said that in order to get the multiplicative inverse mod n, we're going to find that s and then take s mod n. So at this point, our big question is, which one of those is really considered the s in this case? Because we have a negative 8. You see we have these two numbers down here, a negative 8 and an 11. The question is, which one of those is our s? And remember what we said in the last slide. The number in front of the number we're getting the inverse of. We're getting the inverse of 48 mod 35. So it's the number in front of the 48 that would be our s. Okay, so our s is the negative 8. So now remember that s mod n is our multiplicative inverse. So s is our negative 8, so negative 8 mod 35 is a multiplicative inverse mod 35. What is negative 8 mod 35? Remember how we do, how we get a mod when we're starting with a negative number. We start at the negative number and add in as many 35s in this case as possible until we get up into the positive range and then stop. So we just have to add one of them in and we get up to the positive range. Where we end up is the answer. So we end up at a 27. So we would say that 27 is our s mod n, and therefore 27 is our ultimate answer. 27 is the multiplicative inverse of 48 mod 35. Now, let's check. You always want to check here. It's pretty easy to check. So let's just check and see. If we multiply the 48 and the 27 together and then take mod 35, what should we get? Well, remember that the definition of multiplicative inverse mod n is we should get a 1, right? So let's see if we get a 1. 48 times 27 is this number here, 1296. We can use a calculator to take 1296 mod 35, and you find that the answer is 1. So yes, that is true. We found the unique multiplicative inverse of 48 mod 35, and the answer is 27. Now we're going to move into a new lesson called Intro to Cryptography. Cryptography is the science of protecting and authenticating data and communication. A cryptosystem is a system by which a sender sends a message to a receiver. The sender encrypts the message so that if an eavesdropper learns the transmitted message, she will be unable to recover the original message. Okay, so now why did they say she instead of he or she? Well, it's not a big deal really, but it's interesting why this pronoun was used here, and I'll show you next why. So here's this picture of two people, one on the left and one on the right, who are representing the sender and the receiver. So this girl on the left wants to send the message, meet at dawn. Now, we would call the person who's sending the message person A, right? Maybe because that's the first person involved. So we would call that person A. Well, if we're calling this person person A, and we're going to always have these three different people, the sender, the receiver, and the eavesdropper, why not just make up names for them? And believe it or not, this is something that you see in all discussion of cryptography, is that we will call that person A, who is the sender, we'll call that person Alice, okay, the actual name Alice, okay. Then we're going to call the person who receives the message, that would be person B, but let's make up a name for him. We'll call him Bob. And when you look up information about crypto systems, many times you'll see them talking about Alice and Bob, because that's just a standard. Those are standard names for person A and person B. So we're going to always say the sender is Alice, the receiver is Bob. Now, there's an eavesdropper, a third party, right? Well, since this person is an eavesdropper, we're going to call that person Eve. If we had to make up a name, we would call that person Eve. So that's why this paragraph above said she will be unable to recover the original message. Is we're going to think of her as a girl named Eve. Okay, so we've got Alice, Bob, and Eve. And Alice will be trying to send something to Bob, but Eve might be listening in. So the unencrypted message that Alice would be trying to send is called the plain text, and the encrypted message is called the ciphertext. And we'll see some more of that here in some of our examples. The receiver must have what we call a secret key that allows him to decrypt the ciphertext to obtain the original plain text. Okay, so you see this little key under Alice and under Bob. They both have the secret key. So when Alice sends meet at dawn, Bob has that secret key, and he can unlock that message and knows that she's saying meet at dawn. Here's a simple example. We're going to use a system that you may have used back when you were in elementary school. Although these days with text messages, you don't really have to do that. But back in my day, when I was a kid, we only had notes on pieces of paper to send to people, and that's how we got our messages across. So in class, if you wanted to send a note to someone, there might be several people who could intercept that note. And so this was just a kind of an easy way to encrypt a message that sometimes kids used to do. So let's say that Alice wants to send the information to Bob that says time for lunch. Okay, and the underscores mean there's an empty space. So it splits up the actual words. Okay, so what she could do is just write out the alphabet A through Z and start with 1 at the very left and go all the way up to 26. And then for, the space, maybe we could call that 27. And if there's going to be a period anywhere, maybe we could call that 28. So you could come up with that little system there, easy enough to do. Just write the alphabet and put the numbers under there. And then she could start replacing the letters with numbers instead. So time for lunch could become this. First of all, let's look for the T. T is the first letter. Look up T. T is 20. So you see that the first two digits is a 20 under the T. And then the I is next. Look under I. That's a 9. Now, if there's only one digit, we need to put a 0 in front. So we'd call that 09. So you see that under the I, we have 09. So you do that for all of those letters and get this long number. Then Bob would receive this long number, and if he knows that that's what this is all about, he would have a chart just like this, and he would say 20. The first two digits are 20. What is 20? He'd look up and see, oh, that's a T. And what's 09? That's an I, and he would then be able to decipher the message. So he would know that the message says time for lunch. Now Eve, she wouldn't see the time for lunch, she would just see this long number. And the question is, does she know that trick? And since it's a kind of a common trick, that's probably the first thing she would try. So that's probably not the system any sophisticated operation would want to use. But let's say that Eve just does not know about this system, then all she would be seeing is that long number and not know what it meant. So she would just not be sure what that meant. But if she does know the secret, she could decode it too, right? So she could go ahead and find that. So this isn't a real great secure system because a lot of people know about this system. But let's add a layer onto this. Let's say that Alice wants to send this message to Bob, and so she turns it into this long number. But instead of sending that on to Bob, let's say she has some kind of secret in something that she's doing to encrypt this number here. So she would have what we could call a secret key, some information where she would change that number around. And I'm just going to kind of block it out like that. Like maybe it would be totally different numbers. That's an example, but I'm just kind of blocking it out. So it's just like something that is not what the 2009 is, something else. Okay, then she could send that on to Bob. Bob would get this, and that he wouldn't have the original message, he wouldn't have the 2009 message, he would have this other message that somehow has been changed around. But if he has that secret key, then he would be able to decrypt that message and come up with this, and then use that alphabet trick to come up with time for lunch. So that's a little bit better than what we talked about a second ago, because at least there's some encryption involved more than just that little alphabet trick. So there was a secret key, and so only Bob, who knows the secret key, could be able to decode this. Now Eve, she would just see this encrypted stuff. And if she doesn't have the secret key, she has no way of unlocking that. So she would not be able to know what the message said. So what could we use for that secret key? We're going to talk about this. This isn't anything that you would have come up with, on your own at all. This is something that's been figured out ahead of time. This isn't the RSA cryptography system. We'll talk about the fact there is still a little bit of a problem with what we're going to talk about next, but it's much better than just using that plain alphabet trick, right? We're going to learn how to use a secret key. Okay, so let's say that again we have this message, time for lunch, and it translates into these numbers here. Then here's what we're going to do. We're going to come up with this n that is a number at least as big as the largest plain text number will be. Now, this here would be considered plain text. We said the unencrypted text is called plain text. And then we're going to use a secret key to encrypt it, and then that will be called ciphertext, right? So here, this is our plain text, this 2009 number, and so we need to come up with a number at least as big as anything that could be. So basically, if all of those were the largest 28, I think 28 was our largest number, we need to come up with a number larger than what the largest of this, any of these messages this size would be. Okay, so we would come up with an n at least as big as that. Now, Alice and Bob would share a secret number, and this number is going to be an integer, and it says in z sub capital N, meaning, remember, z is the integers, capital N means that's as high as we're going. Okay, so k would be some integer 0 up through n, capital N. The security of their encryption scheme rests on the assumption that no one besides them knows this number k. Okay, k is the secret key. So here's the scheme. To encrypt a plain text, and we're going to call that M. So in this case, our M is the 20091305 blah blah blah. To encrypt that, and that's going to be a number in, that's less than or equal to this capital N, Alice is going to compute a new number called C. Okay, so we know M is that big number 2009. K is that secret number K that only Alice and Bob know. And then add those together, take mod N, and that gives Alice a new number called C. M, as I said, was our plain text. That's before encryption. What we get, the number we get for C after adding the K and then taking mod N, that's called C, and that would be our ciphertext. Then Alice would send the ciphertext to Bob. And then when Bob receives that ciphertext, he knows K and he knows N. So he can put the C in this equation, which is the inverse of that first box. And so he'll take the ciphertext, subtract K, take mod N, and he ends up getting the plain text back. And so then after that, he could decode that plain text by, using that alphabet chart. So let's go through an example. Let's say that Alice wants to send we're going to stay small here. Alice wants to send the message lunch. So she would look at that chart with the alphabet and come up with the numbers there that correspond to the letters. And then she would come up with some number that's going to be as big as any of her messages would be. And so she's going to choose this number here. It's a 2 with a lot of zeros after it. Then K, she's going to choose K to be this large number here. It's a number that just has to be smaller, equal to or smaller than capital N. Okay, now what will she do? She'll take the M, which is the plain text, which is the 1221 number, add K, find out what that is, take mod N, and get C from that. So that's the M, and so she would get C by plugging in all of those numbers. And then she ends up with this calculation that ends up being this number here, 332251419. So she sends that on to Bob. So that again is the ciphertext. That's the encoded text. Now he knows the secret key. He knows N and he knows K. So and he knows then that other function that's going to go backwards and go from ciphertext back into plain text. So he would take what he's got, the C, and then subtract K, then take mod N and get a new number M, which is again the plain text, and then he would be able to go to that alphabet chart and find what the message was. So he would do that. Now Eve would just intercept the 332251419. If she doesn't know N and doesn't know K, then she doesn't have the secret key, because the secret key is those two numbers, N and K. So she would not know what to do with that, and so she can't decrypt this at all. So now the N and the K, in case you're saying, well, now how do we get the N? How do we get the K? Remember, N just has to be a big number that's as big as any of your plain text would be. And then K just has to be any old number the size of N or smaller. And I say number, I mean integer. Okay, so you just come up with your own N and come up with your own K, and then you've got a secret key. So both Alice and Bob know that secret key, so they can come up with, so they can encode and decode with no problem. Eve, on the other hand, does not know what that means. So this scheme that we just talked about is fairly simple, and it's an example of what we would call symmetric key cryptography. In something called symmetric key cryptography, Alice and Bob, the sender and receiver, must meet in advance or communicate somehow over a secure channel to decide on the value of the shared secret key, right? Alice and Bob need to already have come up with that N and the K. Now, think about this. Well, if Eve can intercept their ultimate message, couldn't she possibly intercept their communication in coming up with N and K, right? So that's the problem, is that they've got to, Alice and Bob have to somehow come up with N and K without Eve hearing about it. So that's just something to keep in mind. If that can be done, if Alice and Bob can somehow get that known to each other without Eve finding out, then this can be done. Okay, so the requirements are here. This is just some simple encryption scheme requirements. Basically, don't worry too much about this. We're not going to need to use it too much, but it's just saying that no two distinct plain texts map to the same ciphertext, and that the decryption scheme is the inverse of the encryption scheme. So basically, when you use this, and this example that we did with in the light blue boxes is just an example of a simple encryption scheme. It turns out that these two requirements do exist, that we don't have two different plain texts mapping to the same ciphertext, and we know that when something's encrypted, then it's always going to be decrypted back to the original thing. That's all that's saying. I need to make one point about this simple scheme that we've been talking about today. And that's all we're going to talk about in this lesson is how to use this scheme that I've just talked about. Again, it's not the RSA cryptography. It's not foolproof, right? Because we've said that the problem is that if if Eve can intercept the actual message, maybe she would have been able to intercept the communication when they decided on N and K. So that's why this isn't foolproof, and RSA is much closer to being foolproof than this. But so one thing about this type of decoding and encoding is that, let's just say we want to send a simple message bud, B-U-D. Then let's go through this process that we just did. We could say bud is 022104. That's using the alphabet up there. Then now, since this is a number, and remember, we're putting this number that we get, this plain text number M, into a calculation, then we'd be dropping that leading 0, right? Because a real number doesn't start with 0. So what we would end up with is the 22104. Then Bob would eventually decipher that ciphertext back into plain text, and he would end up getting the 22104. Now, what he has to do, if he just saw that, he would go, okay, the first 2 digits are 22, so he would go to the 22, and that's a V, and then he'd go to 10, and that is a J, and then there's this 4 by itself, and he'd go, well, what's that? You know, all of the alphabet has 2 characters, two-digit numbers associated with them, so there's an 04, but there's no number just called 4. So he would not get bud like Alice originally intended. So here's the problem. It was because of that leading 0 that got dropped that he didn't even get this right. So here's the bottom line, and it's not that hard. The receiver, using this simple cryptography system that we've just talked about, using these 2 specific equations to take the plain text and go to ciphertext, and then ciphertext go back to plain text, the receiver should always be aware that a leading 0 could have been dropped. So here's the solution. It's an easy solution. He should count the number of digits in the plain text, not in the ciphertext, but in the plain text. So after he deciphers it, then he should count the digits. So he would get the 22104. He would count 1, 2, 3, 4, 5. If the number of digits is odd, then he should add a 0 at the beginning, because any of the plain text should end up being even number of digits. So that's what he should have done. He should have said, wait, there's only 5 digits, so I'm going to put a 0 in front, and my plain text will be 022104. Then he would have been able to decipher that correctly. Okay, well, that is it for this lesson. Next time we'll get into the RSA cryptography system, but for now we've learned at least just a simple system that could be used.